In Chapter 15, we discussed a little bit about the Fourier series. And I'd like to dive a little bit more into that now that we're talking about sound, because there are many applications that we find using the Fourier series and this idea of sounds. Now, for the Fourier series, the series requires a repetitive or periodic signal. If it's not periodic, then there's another Fourier process called the Fourier transform that will need to be used. But we're just going to talk about a periodic signal, meaning specific tones, uh, a sound that is constant. So if I have some function f of t and I want to break it down into different components of sines and cosines, well, the first thing is I'll have a term that's just going to move it up or down the y-axis, and then I can represent this function by this formula of f of t equals a naught times, or a naught plus the summation of some constant an cosine of 2n pi times t over the period plus some constant for coefficient for the sine term and 2n pi t over the period. So with the Fourier series, we need to be able to find the coefficient a naught and then a sub n and b sub n. And these coefficients then are in terms of the harmonics, because you notice that we're just looking at harmonic frequencies of both the cosine and the sine, and these coefficients and the different variations will produce a specific signal or representation of. To calculate a naught, we use the formula 1 over the period times the integral of 0 to integrate across the period f function of x dx. And notice that this is just the average of the function. A sub n is equal to 2 over the period times the integral from 0 to t of f function of x times the cosine of 2n pi t. Oh, I'm sorry, I should use x because we're doing the Fourier series in terms of x here. X over t, and b sub n is 2 over the period times the integral of 0 to t function times the sine of 2n pi x over t. And I forgot my dx here. So these are the methods that we use to be able to come up with a Fourier series. Now, I'm not going to mathematically prove why this works. I'm hoping to show by illustration why this is true. And here I've created in MathCAD this formula, or the Fourier series, And here's my function, f function of t, and I just put a formula in here. And you know that it's periodic. I'm basically just using this function as an example. And notice that all my coefficients are 1 for everything. Actually, for the sine, it's -1. So I have the computer go through and calculate the Fourier series. The blue line, which is behind, is the actual function f of t. The red is the Fourier series. And notice that the coefficients line up. The blue are the cosine coefficients, a sub n, and the red are the sine coefficients. Now let's change the coefficient for the cosine, and let's make it 1 over n, and for the sine we'll make it 1 over n squared. Give it a little time to recalculate. And we're just doing to the 10th harmonic here, so hopefully it won't take. There we go. And you notice that our cosine functions, coefficients, are going as 1 over n, and our sine is on the negative side, but it's going 1 over n squared. And you can see how it follows the path of the plot, f function of t. Now, the power of Fourier is not just doing these kind of uh, signals that are cosines and sines. They're actually useful for others. Now I've defined some functions here. One of them is called a stair function. And you can see that this function is discontinuous. There are these jumps, these huge gaps in the function. But the Fourier series can handle these jumps and can approximate fairly well over these jumps. Now you notice there's a little bit of overshoots when there is these little jumps. That's called the Gibbs phenomena. It actually gets a little bit worse as you increase the number of harmonics, but it's close enough to be able to approximate this function. And notice the function is all sine. There's no cosine coefficients. And you just have the A naught, which is the average value of this waveform. Now another one that is very common is the square wave. And in this case, all of the sine coefficients are 0, and the cosine coefficients, some are positive, some are negative, but they're getting smaller and smaller as you continue down the graph. And you can see the Gibbs effect even more here in these points where there's the discontinuity. You see these overshoots. Another waveform is called the saw. It is also a discontinuous function, but it's a slope function or a slant. And again, at the discontinuities, you see the Gibbs effect at both the top and the bottom. And the coefficients in this case are all sine values. There are no cosine values. A similar one, and it's basically a It's a continuous function. It's not discontinuous. And that's called the triangle. And there are no effects because it's a continuous function. There's no Gibbs effect at these transitions. You see how nicely it follows this path. And let's do, as one last example, let's do a periodic parabola. So in this case, we see even as an x squared function, Fourier will be able to find sines and cosines to be able to follow or approximate that function. So Fourier series, very powerful. We'll talk more about why it's very powerful in the next video. But it's important that you have confidence that the Fourier transform, or I'm sorry, the Fourier series actually works. That it does give a good approximation of signals that we look at when it comes to different sounds.